All right, welcome back to our 5.9 lesson. In our last video, we left off talking about powers of I. I would suggest putting a table like this in your blue sheet you can use on the quizzes. One defining that I to the first is just I, and I to the second is -1, and so on. And also talking about that anytime we have a I to the power of z, well, we would say then that we take our z minus a multiple of 4, so 4, 8, 12, 16, any multiple of 4, and we get w. I to the w then is going to be equal to I to the z. So, quick example, if we had like I to the 9th, well, we'd say 9 is our z, minus 8 is our multiple of 4, 4, 8, and then that equals w is 1 in this case. 9 minus 8 is 1. So I to the 9 equals I to the 1. And from our table, we see that I to the 1 is I. So both of these then just equal I. Moving on now with our equations with imaginary solutions. And sorry if this one's kind of hard to see based on the slide. It's 5y squared plus 20 equals 0. Well, to solve this, we're going to do the same thing we've done to solve other equations. We subtract 20 first from both sides. Leaves us with 5y squared equals -20. Then what we would want to do is divide by 5, and that would leave us with y squared equals -4. Now at this point we would say, okay, we want to take the square root of both sides to get it down, because we have the square root and then negative. That's going to leave us with y equals the square root of -4. Now normally before we'd have said no real solution because of the -4. But now we know that we have to break up this square root of -4. We would say, move it up here, y equals square root of -1 times the square root of +4. And we know from Renee that square root of -1 is I, and our square root of 4 is 2. So we'd say y equals I2. But remember, when we write this in good grammar, our real friends come first, our imaginary friends come later. So we would say y equals 2I in that case. Moving on, here's where we're finally talking about what a quote-unquote complex number is. A complex number is any number that can be written in the form a plus bi, where a is a real number, and technically so is b, but I is that imaginary unit. So a is called the real part, and b is called the imaginary part. So, as you can see in our little table here, examples would be like 7 plus 4i, in which case our a equals 7, which we found from right here, and our b equals 4. So those are both real numbers, 7 and 4, but because we're multiplying 4 by I, that's our imaginary part. Oops, I want to erase that. There we go. So yeah, other examples would be like 2 minus 6i, which is the same as saying 2 plus a -6i. So in this case, our a is 2, and our b equals -6. So, looking at this Venn diagram, anytime that we have a plus bi, well, if we said that b was 0, that would be written like a plus 0i, and 0 times anything is just 0, so we get rid of it. So we'd just be left with a. We know that a is the real part, so that's why in here, wherever b is 0, they're just called real numbers. They're only the real parts of it. Now, the imaginary numbers is whenever b does not equal 0. So that means we have an imaginary part. So if b doesn't equal 0, and let's say that a didn't equal 0 either, so we'll just say both of them are 1. So we'd have 1 plus 1i. So this is an imaginary number, or a complex number, because it has both parts. A pure imaginary number would be where a equals 0. So in this case, we would have 0 plus 1i, in which case we would just have I left. Or let's say it was b was 2, so that would become 2i. These are pure imaginary numbers because there's no real part, it's just the imaginary part. So, knowing all that, that makes this joke, again, super hilarious. I is telling pi, hey, be rational, because pi is irrational. And pi is telling I, hey, get real, because I is imaginary, it's not real. So again, another super hilarious joke. When we want to find values of x and y that will make these complex numbers equal. So again, we have our complex numbers. This is our real part. This is our imaginary part because this part has the I. This is just real numbers. If we want to make them equal to each other, all we do is simply set this part equal to our real part over here and set our imaginary part equal to our imaginary part over here. In doing so, we create the equations 2x equals negative 14 and the equation y times I equals negative 3 times I. Well, when we wanted to solve this equation, we would probably say just divide both sides by 2, and we'd be left with x equals negative 7. When we want to solve this equation, we could just divide both sides by I, in which case we would be left with y equals negative 3. And in this way, we would solve those equations for x and y. Adding and subtracting complex numbers is going to be similar to adding and subtracting our binomials with the variables. We add our imaginary parts and we add our real parts. So in this case, 3 plus 2 is 5. 5i minus 4i, or should I say 5i plus a negative 4i. So when you have a minus here, it's the same as saying, or should I say when you have a negative here, it's the same as subtracting it. So 5 minus 4 would be 1. So we'd say plus 1i, or we can just simply say 5 plus I. We don't need that 1 in front of it. Similarly, when we subtract them, again, we have to remember to switch the signs, but it's the same idea. In this case, we would be left with 4 minus 3, which equals 1. That's our real part. A negative 6i minus negative 7i. When we are minusing and negative, that would be like adding. So negative 6i add 7i equals, well, negative 6 plus plus positive 7 is positive 1i. So in the end, here's our real part, here's our imaginary part, so we'd say that it's 1 plus 1i, or 1 plus I. Moving along to multiplying complex numbers. Again, like our binomials with the variables, we have to FOIL this. So if we look at our first ones, 1 times 7 is 7. If we look at our outsides, 1 times negative 5i is negative 5i. If we look at our inside numbers, 3i times 7 is positive 21i. And if we look at our last numbers, 3i times negative 5i, 3 times negative 5 is negative 15. I times I would be I squared. Okay, now from here we want to combine our like terms, but we also want to realize that, like Renee said, I squared is actually negative 1. So 15 times negative 1, this is actually a plus 15. So Working from here, we have 7 plus 15. Combining these like terms, we have 21i minus 5i, or negative 5i plus 21i, becomes a positive 16i. We're not quite done because we still need to combine these like terms, which leaves us with 22 plus 16i. And that would be our final answer there. In this last bit, we're going to talk about dividing out these complex numbers. Now, in this case, again, this looks very similar to our rationals, when we had a number with a rational and we wanted to rationalize the denominator. In this case, we want to, we'll call it realize. We want to realize the denominator, in which case, like before, we have to use a conjugate. What's this, a J? Conjugate. These ones are a particular kind of conjugate. These are a complex conjugate because we are using the conjugate of a complex number. So if our denominator is 3 plus 2i, our conjugate, and we're going to be multiplying it by, get this out of the way, is going to be 3 minus 2i. And just like before, we need to multiply it on top as well. So the 3 minus 2i on top. Now we know how to multiply our complex numbers. 3 and 3 make 9. 3 minus 2i, or 3 times a minus 2i, should I say, is a negative 6i. 2i times 3 is a plus 6i. And 2i times a minus 2i is negative 4i squared. Now again, Renee told us that this is actually negative 1. 4 times negative 1 is positive 4. We notice that our negative 6i and our positive 6i subtract out, so we're left with just 9 plus 4. So we know that our denominator, I'm going to work down here, becomes 13. Now in this case, we're looking at our numerator. Let me get rid of this. So we have 5i times 3 becomes 15i. 5i times negative 2i becomes negative 10i squared. Again, in this case, Renee told us that this is negative 1. So negative 10 times negative 1 is a positive 10. So we have 15i plus 10. And this is our final answer here. Working on this one, this doesn't quite look like our irrational ones from before because we don't have that binomial on bottom. It's just the one term. So I guess it does kind of look like the rational ones where it's just a rational on bottom with without the binomial part, so there wasn't two terms there, it's just the one term, in which case we would just multiply by that radical. So in this case, we can just multiply by I as our way to realize the bottom. When we do that, 5i times I becomes 5i squared, which again, Renee told us that's negative 1. 5 times negative 1 becomes a negative 5 on the bottom. On the numerator here, 4 times I becomes 4i. Negative I times I becomes negative I squared. Again, Renee told us that this is negative 1, so a negative negative 1 makes a positive 1. So we're left with 4i plus 1. And this would be our final answer here. If we want to simplify that, we can notice that we have a minus here, or a negative sign. We can pull that out to the front, and we would be left with 4i plus 1 over 5. Both are acceptable answers. And that concludes complex numbers.